understand that 3 over 6 is numerically equivalent to 1/2. That's easy. So we've been taking rational expressions. Yeah, don't even. So if I had the rational expression x squared plus 6x plus 36 over x squared plus 5x minus 6, this is just a whole bunch of fractions, right? If you plug in 1, you get some fraction divided by another fraction. If you plug in 2, you get a different fraction. You plug in 3, you get a different fraction. What we're going to do is create a graph that represents all fractions, which is easy because we're just going to ask our calculator to do it for us. But, hang on, you'll want to pay attention to this. Okay, so if I factor this, I get x plus 6, x plus 6, oh, I'm sorry. Hey, now it works. Okay, so the lesson for today is if your universe doesn't work, just erase it and change the number. So, okay, now I'm going to cancel these, and I'm going to make the statement that this first rational expression is identical to x plus 6 over x minus 1, right? I'm going to create a graph full of fractions, right? Well, all I've done is simplified those fractions ahead of time. So let's say that my graph, I plug in, my first one would have been like 4/12, and my second one would have been 5/15, and my third one would have been 6/8, well, I don't know, 6/18, whatever. And all of these simplify 1/3, well, they end up all being 1/3. That's probably not what I wanted to do. Okay, forget I did that. See, just erase your universe and start over. So let's say 6 over 10 and 8 over 8. So let's say these are 3 of the fractions I created. Well, they need to be simplified. 1/3, 2/5, and 1. Right? So all I've done is simplified before I plug in my x's. Does that make sense? So instead of calculating these numbers, I'll calculate those numbers. 3/5. Sorry. I brought my A game to school, didn't I? Okay, now, everybody agrees we would much rather graph this. But we did eliminate one part of the graph that we need to remember. So yesterday we talked about discontinuities. Where are the places that x is not allowed to be? So if we look down here, the root associated with that is -6, and the root associated with this is 1. So I can plug any number into that rational expression except -6 and 1. If I plug those in, I get infinity or negative infinity, depending on how you plug them in. Okay, so in this graph here, what am I not allowed to plug in? Just 1. X is not allowed to be 1. So by simplifying the rational expression, I eliminated one of the discontinuities. Does that make sense? So the only difference between these two graphs is 1 point. The new equation has one more point than the old equation. Does that make sense? But here, x minus 1 still exists, so there's a discontinuity at 1. And when you're dealing with rational expressions, there are two types of discontinuities. The first one, and please giggle because it's really funny, is called, we haven't even done, the first one is called an asymptote. There's Amy's going. She's giggling. I once saw a cartoon. I actually think it's on one of my web pages. And it's these two Greek guys in togas, and they drew a triangle on the ground. And one of the guys says to the other, "You might be right, Pythagoras, but if you call the hypotenuse, everybody's going to laugh at you." You apparently don't get it. But it's, or it's just not funny. Yeah, it should be asymptote, not hypotenuse. But you guys know what a hypotenuse is, right? No, it's an occupied toilet on an airplane. That's what it means in Greek. Is an There we go. I got a couple of laughs. Okay, back to math. An asymptote. An asymptote is a line. Well, in this class it's a line, but it could actually be a parabola or anything else. But it's a line that a graph approaches but never reaches. We've seen these before. So that would be an asymptote at x equals -2. And it might look something like this. The graph's going to come and get really close, but never touch. Okay? And then on the other side, it might start really close and then go like this. All right? If your discontinuity does not factor, it corresponds to an asymptote on the graph. If your discontinuity does cancel, then you get what's called a hole in the graph. So the graph is chugging along and it jumps over one number and then keeps going. Amy is the queen of bodily humor. Okay, so the bad news is your calculator will not find the holes for you, at least not in a very easy way. Okay? Because your calculator, all it does is draws a bunch of dots, and those dots are so close together that it looks like a line. So if I had a line and I'm missing one of those dots, am I going to be able to see it? No. So the calculator is going to draw a line straight through that gap. But in reality, the graph gets close to it, jumps over a single number, and goes. So the way we represent that is we put a circle in that spot. And that represents a single point discontinuity. It's kind of like a not equal to sign. So it goes to that point, jumps over, and then continues. So if we look at this graph, we have an asymptote at 1 because this factor did not cancel, and we have a hole at -6. Other than that, the two graphs are exactly the same. So I'll show you what I mean. When you graph rational expressions, the numerator needs to be in parentheses, and the denominator needs to be in parentheses. If you forget that, it's just not going to work. So let's graph x squared plus 12x plus 36. Divide that by x squared plus 5x minus 6. So you see how the numerator, Katie, the numerator and the denominator are both in parentheses. So we push graph. So you see the asymptote at 1, but you don't see the hole at -6. If you go second calc, there the hole is represented by an error. And if I go down to 1, then there's also an error at 1. So you can look at the table and find the holes, but memorize this graph. See how it looks? So I'm going to go in, and now I'm going to graph x plus 6. Oh boy. And then divide that by x minus 1. And it looks exactly the same. And if I go into the table, the hole is not going to be there. The asymptote's there, but the hole says 0. Whereas before it said error. So I'm going to give you back your assignments that you handed in that have all of those simplified equations, and then we're just going to state the discontinuities and graph them. Oh! Okay, so let me pause this and I'll... All right, let's look at a couple on your worksheet. For some reason, the easy ones on the front confuse people. I don't know why. They're the easiest ones to do. So look at number 1. We simplified it to be negative 6x over 7. So that's what we're going to graph. So I'm going to go to y equals. I'm going to graph negative 6x divided by 7. Oh boy. Negative 6x divided by 7. Oh my goodness. Is your plot 1 turned on? Go to y equals. Is your plot 1 at the top highlighted? So this is a straight line. But did I eliminate any x's in the denominator? Yes. So whenever you eliminated x's in the denominator, you're going to have holes. So what number would have made the denominator 0 before I simplified? 0. In fact, you actually have 2 zeros, right? It's 42 times x. So it's 0 and 0. It's like a double. It has a multiplicity of 2. Well, what's the difference between a whole with multiplicity 1 or one with 2? Nothing. Okay, so yeah, just circle it bigger, I guess. So look at number 2. Number 2, we had 16RR over 16RRR, and those cancel, so my graph looks like 1 over R. Did I have any R's cancel? Yes. So it's really like x cannot be 0 or 0 or 0. These first 2 zeros represent what on the graph? What structure, holes or asymptotes? They canceled, so they'd be holes. What does this remaining R? So can you have a hole and an asymptote at the same time? Tom told me this morning when we were talking about which lessons we were going to teach, and he said, if you don't have a hole in your asymptote, you have a problem. Okay. So apparently you and Tom have the same humor level. So you're like 7. Okay, so if it happens where you have a root with multiplicity 2, if you have a root in the denominator with multiplicity 2 and one of them cancels and one of them doesn't, can you draw an asymptote and a hole at the same time? Well, you can't. There's nowhere to circle, right? Because the asymptote is a line that represents where the graph doesn't reach. So you can't circle it anywhere. So if you have both, asymptote always wins. Okay. Yes, asymptotes trump. Okay, look at number 12. So 12, we get x plus 6 times x minus 1. The x plus 6's cancel. Where are my discontinuities? X is not allowed to be negative 6 or 1. Okay? Negative 6 is what structure? It canceled, so it's a hole, and 1 is an asymptote. So when I graph this, oh my goodness. So I'm going to graph 1 divided by x minus 1. And the asymptote will show up So when you put this on your graph, you need to state the discontinuities, just like we did yesterday. And then I'm going to have a hole at -6 and an asymptote at 1. And it's usually a good idea to represent your asymptotes by a vertical dotted line. Some of your calculators will draw a solid line. If you have an older calculator, it will draw the line. Yeah. So just state the discontinuities and then draw the graph and make sure that the hole is there. Okay? Look at 25. So I believe this is x plus 10, x minus 8, 2x times x minus 8 times x minus 4. If I did that in my head correctly. So the bottom is an x to the third, so I should have 3 discontinuities unless there's a multiplicity in there. So my discontinuities are 0, 8, and 4. Does everybody see that? Right, so this is the 0. My 8's cancel and my 4's don't. So on the graph, I'm going to have an asymptote at 0 and an asymptote at 4. And I'll have a hole, and a hole at 8. And I believe the graph is going to look like this. And then my guess is this way. And that's what it would look like. So it's super easy, unless you didn't do the worksheet. Then you got to do it and answer this one. Some of you have to play catch up.